Hello, this is Mr. Thomas here. I'm going to go over quiz number 2, and I just kind of want to quickly kind of go over some of it just to give back some feedback. I'm going to begin grading really soon, probably tomorrow, and finish everything by Saturday morning. And I've just been really thinking about the quiz and wanting to get to it and kind of go over it myself a little bit. So what I'm going to do is um, quickly just maybe do a few problems from the quiz and see how it goes. So number 1, it says state the domain for each function. And we have f of x equals 1 over x plus 3. And that is my inverse function. And recall that an inverse function is something with 1 over the x where x cannot be equal to 0. If we have 1 over 0, this becomes an undefined expression is what we call it. It has no value. The value is just undefined. If you try to divide by 0, there are any numbers. You can put any number in here. With 2, 3, 4, 5, you're always going to get 0. And so for that reason, it's an undefined expression. And so for this function, if this was my function, x cannot be 0. We know what happens when x gets close to 0. The number gets very large. But when it's actually 0 itself, it's an undefined expression. And so if we eyeball this, if we look at the denominator there, clearly x cannot be -3. If x was -3, we'd get a 0 on the denominator. And so the way to actually break this down is take the denominator, set it equal to 0, solve the equation. It turns out that x is -3. And that is our restriction. And remember, the domain represents all x values for which the function is defined for. And so it turns out that this function will accept any real number and give back a real number, except if x is -3. And so for that reason, our domain, and it's time to just state the domain. And so one way to state it would be to write it out as a function or as a set. And so we have the set of all x's such that x is not equal to -3. And this is sufficient. This basically, this is clearly stating the domain, because the domain is the set of all x values, all input values for which the function or the rule is defined for. And so it's true in this case as well. It's the set of all x's. We know we're talking about real numbers, so you don't have to state that x is a real number. The variable x is defined as a real number. And so it's the set of all x's such that x is not equal to -3. Okay, let's move on. Well, clearly there are no restrictions. We can put any real number into our x as an input value, and we'll end up getting a real number. 0, -1, -2. It turns out this function will only report back positive values. So the range is from 0 to positive infinity. However, the domain is what we're focusing in on. And it appears that the domain is all real numbers. And so all you'd have to say is that the domain are all reals. And that's pretty sufficient enough. And again, it is the set of all reals. And you can write it out as a script script R, and that's sufficient. And we have C, f of x equals the square root of x. And it turns out, remember, square roots are not defined for negative numbers. You can take the square root of 0 and get 0, anything greater than 0, but you cannot take the square root of a negative number or anything less than 0. So if you have x is less than 0, my expression is undefined. I can't take f of negative 2, for example. I'd get the square root of negative 2. And that is undefined. And so the domain is essentially all x values are greater than, so it's the set of all x values such that x is greater than or equal to 0. And of course, there are other ways to write out the set, and I'll accept anything that is equivalent. And you can even write it out. I mean, you could even say that the domain are all real numbers except negative, anything less than 0. The compact interval notation, we're going from 0, so I have to use a bracket. That means I'm including 0. And then everything greater, so that would be infinity. And so these two are the solutions there. And you can just use one or the other. You don't have to list it out in more than one way. All right, let's move on. Evaluate the piecewise defined function at the indicated value. And so a piecewise function, it is a function, but it's kind of divided into 3 different sections. So this particular function, it appears to be and is defined for all real numbers, all x values less than negative 1. So if x value is less than negative 1, you would follow this rule for the function. If x is between 1 and 3, you would follow this rule. And if x is greater than or equal to 3, you would follow this rule here, which is a linear function, slope negative 1, y-intercept 5. And so this is just a matter of looking through each one and evaluating accordingly. So f of negative 2. So we need to evaluate our function at negative 2, which means our x value is negative 2. So which one will we use here? Well, it turns out negative 2 is strictly less than negative 1. So we'd evaluate our function at 3 minus x squared. And what will we get if we plugged negative 2 into 3 minus x squared? And so our x is negative 2, and then we're squaring it. So we get 3 minus 4. And 3 minus 4 is just negative 1. So therefore, you can recap. It's always best to be as precise as possible. Because we wrote it out long, it's always good to come full circle and just say, therefore, f of negative 2 is negative 1. What would happen if we do f of 2? Well, first of all, 2, the x value of 2 is between 1 and less than 3. It's greater than 1, less than 3. And so we evaluate our function f of 2 for 2x. That will give us f of 2 is therefore 4. And also f of 4. To evaluate f of 4, we would use this function here. And so this is part C. This is like by A, B, and C. F of 4 would be 5 minus 4, and that's positive 1. Okay. Of course, you would want to show your work, show your steps, in case you've made a tiny error somewhere. You can earn partial credit, and it's just good test taking skills, to show your thinking. This is a formal assessment of what you know, and so you want to be as clear as possible. Okay, explain what is meant by the vertical line test. And so basically you're going to, of course answers will vary, but you do want to show that you know that the vertical line test tests graphs to see if they're functions or not. And it turns out if I have the xy plane here, I'll say there's x, there's y, and I'll just draw this function here, or this graph. I can't say it's a function yet. It's a relation. I'll call it f. So we have this on the xy plane, we have this f, and the question is f a function or not? And so one thing we'd have to do is conduct the vertical line test. If you can put a vertical line somewhere along the graph such that the vertical line intersects the graph in two places, then it is not a function. Okay, so this is not a function. So wait, let's see. And it really implies, the reason why this method it works is because it implies that there are two coordinates on the function that have the same x value but have a different y value. So there's 2 points, 2 ordered pairs on my graph that share the same x value or input value, but it goes to 2 different y values. And in this case, if this were to be, say, 5, this would be a negative, say, -2 or -3, 5 comma -2 or 3, and this would be 5 comma maybe 5. And so in order to be a function, you cannot, your input value must go to a different output value. You can't have 2 input values going to 2 different places. If you have 2 input values, they should definitely be going to the same place. And so it is just not a function, and this shows why. Let's move on from there. Let's look at number 4. It says, for the function f of x equals x minus 2 quantity squared, find the average rate of change between x is 1 and x is 5. And so that formula, the average rate of change, is just a matter of finding f of 5 minus f of 1 over 5 minus 1. Okay, so f of 5, let's see. F of 5, if I substitute 5 for my x and plug it in, I get 5 minus 2 is 3. And so f of 5 would be 3 quantity squared. So that's 3 squared. F of 5 is just 9. Minus f of 1 now. So let me substitute 1 in for x. F of 1 would be 1 minus 2 is negative 1. Negative 1 squared is positive 1. Whenever you square a number, whether it's positive or negative, the answer, the product, will always be positive when you square a real number. So we have 9 minus 1 up top over 5 minus 1. And so we get 8 over 4, and that reduces. 8 over 4 is just 2. Okay. Circle either true or false for the following problems. To graph y equals f of x plus 2, shift the graph of y equals f of x to the left 2 units. And that would be correct. Okay. Remember, if we have some function, like if f of x was, oh, let's just make believe f of x was x squared. We know how to graph this, but how would we graph f of x plus 2? Well, let's look at what does it equal. It'd be and so if I have this one, I could just graph this one immediately just by moving it over to the left twice. Now, when you have a positive 2, you'd have to plug in a negative 2 in order to get it back to 0. So in fact, the coordinate pair negative 2, comma 0 is the vertex point, and that's where the graph would begin. And so the first one is true. True or false to graph y equals f of negative x. Reflect the graph of y equals f of x in the x-axis. Is that true or false? That is false. You actually, if you have y of f of x, and all of a sudden you're changing your x values. So if you had positive 2 for x, you plug it in here, you're going to get a negative 2. It is now reflecting across the y-axis. So it's reflecting in the y-axis. And then finally, if we're given y equals f of x, how would we graph this? Well, since it's subtract 3, that will actually shift the function down 3 units. That's true. Okay. Yeah, so we're just getting on down and taking a look at the rest of this. It was doable. I think there was a time constraint the bottom and start working our way up really quickly. Using set A, B as domain and range respectively, give an example of a function such that its inverse will not be a function. And so I'll just make a quick function. I'll just say I have this point 1, this point I'll call it 2, and this point I'll call it 3, and one more else, I'll call this one 4. And here I'll say A, B, C, and I'll just say D. And so first of all, a function, well, I'll just start off with what wouldn't be a function. If I have two x values, well, I'll just say, if for it not to be a function, if I start with this one input value, which is 1, the point 1, if the point 1 goes to two places, so let's say it goes to A and also to B, then right away it will not be a function. It will not represent a function. A function cannot do that. However, you can have two separate input values going to the same y. That's okay. All right. And so, of course, my functions going from A to B is my domain and range. And then I need to create something such that if I reverse it, if this is my domain now and I'm going backwards, it will not be a function. And so what we're going to have to do is make this one go to 2, 1 go to B, 1 is mapped with B, 2 is mapped with B. We'll make 3 mapped with A and 4 mapped with D. This is a function. However, now, if we go in reverse, if we look as this is the domain and there's our range, the inverse would not be a function because of this pair here. It's going to two different values. And so therefore, this would be an example of a function such that its inverse would not be a function. It's okay to have two, we call it many to one, but you can't have one to many. And so because of that, that's an example. And if you wanted to steer away from the sets, it's totally possible. I could have actually created ordered pairs to represent my function. I could have wrote a set with the ordered pair 1 comma B, 2 comma B, 3 comma A, 4 comma D, and then its inverse, I flip it around. My inverse would be A comma 3, B comma 1, B comma 2, and then D comma 4. And then you just identify, because the B is going to two different output values, it violates the rule of being a function. And so it's just not a function at all. Number 9, let f of x equal 1 over x. Show that f inverse of x is f of x. And so we need to test that. Let's see if it's true or not. Is f inverse of x 1 over x? Well, there's that rule that if you take f composed of its inverse, you should get x. So there's a question mark. Is it true or not? Well, let's check. Let's do that. F of, well, f inverse, we're checking to see if f of f inverse is x over x, is 1 over x. Now we got to plug it in. I'm using parentheses to show that I'm substituting 1 over x inside of the x. And now we need to divide. 1 divided by 1x is just x. And so this is correct. This works. Another method as well was we could have let y equal 1 over x, switch the x and the y variables, and then solve for the other one. I'd get x is equal to 1 over y. And then as I solve it, you can just swap them out. And yes, there's an arrow. So it turns out that it does. The inverse of 1 over x is equal to 1 over x. Y equals 1 over x. And the truth is that this is called the inverse function. And so that's why it is its own inverse. And the name says it all. F of x equals 1 over x is indeed the inverse function. Okay, find the inverse function of f of x equals 3 minus 5x. So let's let y equal 3 minus 5x. And so now the procedure is interchange the x and the y. You just switch them. In order to find the inverse. And now you have to solve for the y. Okay, so what I'm going to do is move my 5y over and move my x over. So I'm going to get 5y is equal to 3 minus x. And now I need to solve for y. So y is just going to be equal to 3 minus x all over 5. And so I would now say, so f inverse of x is equal to 3 minus x over 5. A little bit of algebra, but it's also important to understand the procedure. Finding the inverse function is something that is important. It's good to know, and there's probably a lot of other ways one could have shown or found the inverse function. And this, we could actually break this down where it appears that the slope is negative 1/5 and the y-intercept is positive 3/5. And so that should be consistent with the graph as well. Okay, just real quick, explain what is meant by the horizontal line test. And this is the test to see if a function is one-to-one. It turns out if you, I'll just use my example here. I have the coordinates x and y, and then I'll call this f, my function f. If I can put a horizontal line through my function, and that horizontal line hits it in two places, here and here, I've showed that f is not one-to-one. And that's all. And remember, one-to-one basically means for every input value, you're going to one output value. And so there's the symbol for one-to-one. And so I have the same, I have two different output values. Let's say I can just make believe that this is -2 and this is 1. They're going to the same output value. So I have two different input values going to the same output value. That is not one-to-one. In order for a function to be one-to-one, it can't happen. And so this function, even though it is a function and it will pass the vertical line test, it fails the horizontal line test. So it is a function that is not one-to-one. All right. let's move on. Let's move on. Well, just real quick, g of f of 1, and so you got to work your way inside and then kind of work backwards. So the first thing is evaluate f of 1. And so you're going to have to use your f of x function, and f of x is the inverse function. So f of 1 is 1. So now all we got to do is find g of 1. And g of 1 is just 1 plus 2, which is 3. For the next one, you need to find g of 7 this time. Okay, g of, and this should be g of x as well. Okay, g of x is equal to the square root of x plus 2. So first we find g of 7. G of 7 is the square root of 7 plus 2 is 9. So g of 7 is the square root of 9. So g of 7 is just 3. And so now all we have to do is take f of 3. F of 3 would be 1/3. All right, let's look at the last one, f of 4, and then we have to f that. And then 1 over 4. Hey, this is the inverse function, so the inverse of 1/4 is 4. So we have the three solutions for part B, g of f of 1. So therefore you would say g of f of 1 is equal to the square root of 3, root 3. F of g of 7, therefore, is 1/3, and f of 4 is 4. All right, and let's tackle this last one. There's probably not that much space, but find the function f plus g. And so the new function would be f plus g would just be and of course they are not like terms. And I'll just say I'll call the new function h of x. I must make a note that okay, that the f plus g function is equal to h. So in other words, here is my function. So I just found it. Let's keep going. F times g. This time I'll write it like this. And then finally f over g. And so I'd get f on top. That's 1 over x over root x plus 2. And this actually simplifies. So it actually simplifies to just 1 over x times x plus 2. And so there's the third function. And then finally, I have to actually identify what the domain is. And the domain for these is that you need to find the domain of each function separately, and it's the intersection of the domain. And so it's those values that they have in common. So let's break this down. Clearly, this is undefined for when x is equal to 0. So the domain of this function is all real numbers except when x is 0. The domain of this one, and let me just make a note, x is not equal to 0. And then the domain of this are all x values that are greater than or equal to -2. So and now if we combine these together, it actually the intersection of the two sets of all real numbers not equal to 0, and the intersection of all x's greater than or equal to -2, I can now say it would really be the set of both of these put together. It would be the set of all x's such that x is greater than or equal to -2 and x is not equal to 0. And that would be sufficient to show that the domain is the set of all x's such that x is greater than or equal to -2 and x is not equal to 0. The next thing I want to do is do pretty much the same thing here. X cannot be 0, and x, we cannot put in a negative value in our radical. So x cannot be less than -2. So it appears that our domain would be valid. The domain in f plus g is the same domain for this one as well. It'd be the set of all x's such that x is greater than or equal to -2 and x is not equal to 0. So I can plug in anything else, but I can't plug in a number less than -2, and I can't plug in 0. If I plug in, say, -1, or actually -1 is bigger, but like -3, I get the square root of -1 over -3. It's undefined when that happens because the radicals are not defined as real numbers for values that are less than 0. And so finally, I come here now. And so we need to think about this. It's only going to happen when x is 0, when the denominator is 0. So the only restriction is, again, the radical is not negative, but also I cannot get a 0 in the denominator. So this time, the set's going to be a little different. It's going to be the set of all x's such that x is not equal to 0 and x must be strictly greater than -2. X can't equal -2 because if x equaled -2, we'd get 1 over -2 times 0. And that would give us a 0 in the denominator. And so in this particular case, it's nearly the domain of this function is almost like the other two, except we had to exclude the case if and when x is equal to -2. And that's pretty much going to do it for quiz number 2. I hope this was helpful and useful. I look forward to answering more questions about this in the future. And we're going to keep pushing onward. Talk to you later. Bye-bye.